So hi everybody. I'm really happy to have you here, and I'm really happy to have today with us Andre from Causal. He's here to tell us about their platform and a little bit about how it works and what can you do with it. And Andre, I will leave the stage for you. I just gotta say that we usually have questions in the chat, or in the Israeli way, we will just interrupt you and ask. So if it's not okay, just tell us in advance.
Please interrupt. It's actually so much better because if I'm talking, I may not notice the chat. So just speak up. It's okay. Talk over me. It's perfectly fine. Hopefully we could have a conversation more than just me talking. Um, and there's a lot of interesting topics. I am probably starting with something a bit more about the ideas behind it, but I want to be practical. And at any point, feel free to ask questions. I think there's a lot of interesting things to explore. And first of all, thank you very much for having me. This is a lot of fun. And especially, you guys, we've been working with Shemtov for a good couple of months now, and it has been really exciting and hopefully helpful as well. The conversation last week was a lot of fun. My wife approved after the you shared the recording, so I guess it's good. Seriously, I think it was a great conversation. I enjoyed it. Thank you very much. And all right, so let me, start maybe just a bit about myself. So my name is Endre Sara. I'm a founding engineer at Causal. Causal is a new venture that we started about a year and a half ago, and our goal is to help teams to provide resilient application services to operate cloud-native distributed, complex cloud-native distributed applications better, and basically provide software that can accomplish that for you. Prior to this, I spent 13 years at another company that we started in 2009 called Turbonomic. Turbonomic was a closed loop automation systems to manage application resources, the automated application resource management. Was acquired by IBM in 2021. Prior to that, I spent about 10 years at Goldman Sachs. I was responsible for the global application and systems management engineering. And it is really a lot of fun to be able to see it from both sides as an end user and now more lately as a vendor in how large complex environments are being built, architected, developed, and deployed and operated, and how it could help all of us to do a better job at that. So actually, maybe I'll share my screen. Hopefully, you guys can see. Is this the right screen? Meaning the right PowerPoint slide?
Yeah, we can see the presentation.
Good. Okay. So we are. I want to talk a bit about causal AI to begin with. You might have come across among the different types of AIs, causal AI, especially over the last couple of years, has been getting increasingly more attention to enable better decision making, more trustworthy, more explainable decisions in medical sciences, in marketing, in financial portfolio, risk management. But it hasn't been applied to IT. It hasn't been applied to operate applications, and that is what we are in the business of. So I want to give you a bit of a background on what causal AI is, and then use a practical example to illustrate why this is needed to operate and provide resilient cloud or cloud native applications. In general, I believe that people are spending, unfortunately, too much time in troubleshooting and recovering services instead of building and delivering new applications. So really, that causal AI can help to do this. But there are a couple of challenges specific to the application domain that makes it even harder than it is to apply causal AI to the other industries that I mentioned. One of these problems is that these application environments are highly dynamic. If you look at a medical trial, it may take weeks or months, and they go on for a while. But application environments change, maybe not even every hour, every minute, maybe even every second. And the scale of their complexity is large, and it's continuously expanding, which makes it really hard to operate them and to be able to make the right decisions continuously by humans alone. So we're basically saying that this application management needs to change, and we need software to help us to not just observe, but to actually operate applications. There are a couple of interesting aspects where people are just saying, let's just collect more data, do more observability tools. And in our experience, and I'm sure that you guys experience the same, the sheer volume, the cardinality, and the complexity of this data is overwhelming. It is not just expensive, but also a significant cognitive overload to be able to look at all the different traces, all the different metrics, make sense out of them. Meanwhile, all of the applications, databases, infrastructure components, and software versions are constantly changing. So it is really hard to do this humanly, but it's actually hard to do this in software as well, because if you were to apply some AI algorithm that is based on learning a particular application stack, it's impossible. By the time you learn something useful, it changes. So how can you apply AI to any of this that still provides meaningful and explainable results? So what people are trying to do is to, historically that is to apply correlation. But the problem is that that is not causation. You might have heard this. For example, if I observe that my database is slow and my application is slow, is the root cause my database, and I need to scale up my database so that my application is going to be faster, or do I need to change the application and the database is fine if the root cause is in the application? The fact that these slownesses are correlated does not imply causation. And I'll talk about how we approach this problem differently. Another thing that you probably come across fairly frequently, I assume, is that people assume that all of the application issues are caused by infrastructure. If I just give you more CPU and more memory, then everything is going to be fine. And sometimes that may be the case, but not always. And it's really important to understand the causality between, when it is an application problem impacting another application, an application problem impacting the infrastructure, or in the cases where actually it's the infrastructure that's impacting the applications. So in general, I think that prior to causal AI, machines lack the understanding of the causal relationships. And this is the biggest roadblock to giving them human level intelligence. This is a quote from Judah Pearl. If you are interested in learning more about causal AI, the Book of Why is an excellent read. Judah Pearl has really been the leading researcher that kicked off both the concepts as well as the mathematical foundations of how this information can be represented mathematically. And of course, we are applying a lot of that. But the causality is critical, is the point. And I guess even if Gartner recognizes it, that this must be true. Sorry, where basically causal AI is the next wave that is required, and it will enable greater automation, and it will make more sense out of the huge volumes of data that you might already have in your observability stack. So what is causal AI? So we believe that this is basically capturing human knowledge in a structured form that will help software to learn causality, to be able to discover a live environment and apply these causal models to identify the root cause from the observed manifestations. What we mean by manifestations is the various anomalies or alerts that are being generated. And by identifying the root cause, we can automate the remediation of these problems where automation is possible, but at least cut down the mental overhead of troubleshooting and wasting time in trying out different things by quickly identifying the root cause. Um, by the way, feel free to interrupt anywhere because maybe I'm going too fast. I'm sure. Or I could go on. So one thing that someone might ask is that, like, I thought that large language models are supposed to solve all problems. They are the magic bullet. And as it turns out, I am quoting one particular research paper from last year, but more broadly speaking, in its current state, large language models are not able to infer causation from correlation. So practically what this means is that I just throw a bunch of data at, say, large language models. It will not be able to figure out what is causing what simply based on that data. And this is where we believe that the human knowledge capture in terms of causation is important. Now, not to confuse anybody, causation is not correlation, is what I'm saying. But if you already have causation, correlation is not causation, I'm sorry. But if you already have causation, you can actually use the data, use the correlated data, and make your causal reasoning better. So you could use causation to understand correlations. You cannot use correlation to understand causation. And hope it's not too confusing, but yeah, feel free to ask. I actually want to do something more practical. Hopefully this was not overwhelmingly too theoretical. So what we have is a nice little open source sample microservice application that we are using to demonstrate various failures. And then we actually want to detect the root cause of any particular failure. By the way, using Causely, our software, our SaaS service, and then to basically capture and represent these causal relationships um, for this particular application. Of course, the idea that this is just an example application that you could use, I am sure that in each of your respective engagements and daily life, you've got plenty of applications that are failing, hopefully not too frequently, but every once in a while, so that you may not need to have your own little self-created failures, but if you're bored and you want to try something at home, you're welcome to try this. Obviously, I'm constantly updating the documentation. That link on the top is actually a page that you could use to deploy this application in a Kubernetes cluster, where basically the actual application deploys using a Helm chart, and you end up with a set of microservices that are interacting with each other. This is a set of microservices that are both calling each other as well as making requests to a Postgres database and using Redis as a queue to communicate with them, and then we can fail them in interesting ways. Maybe I could switch over for a second. If you guys can also see my web browser, this is the web page that I'm referring to. And actually, let me move on to one more slide, and hopefully this helps. So what we can do with this nice little open source example is to create various application topologies. This picture may represent it a little bit better. We create multiple services running on different nodes in Kubernetes and calling each other. There is a front-end service that calls the add, cart, and the shipping service, which in turn call other, call each other, and of course talk to Postgres and talk to Redis. And what we're doing is we are actually introducing a couple of failures here, which are going to create alerts. These little nice fires are different alerts. The question is that just by simply getting these alerts, can someone figure out what is actually the root cause? And really our point is that if you only look at the alerts and the failures, it is difficult just to figure out what the root cause is. I'll illustrate even further. So our goal is to focus on what is the root cause, what do you need to do to recover this service, and really our definition of the root cause is that if it is correctly identified and the action to resolve it is taken, then it either prevents or a further outage, and of course eliminate the alerts. If I do something and it doesn't restore the service, it doesn't eliminate the alert, then that wasn't the root cause. So here is a couple of things that can happen in this environment. I can get alerts for example, on the node for high CPU and high memory utilization. And at that point, I might think that like, well, that may be just a problem with my Kubernetes cluster. I need to scale up my cluster. I may get alerts about my Postgres high CPU and high memory utilization, at which point I might try to scale up my Postgres or my Redis in terms of like CPU and memory limits. Or I get both of them, and now I try to scale out both the cluster and both the Postgres and the Redis limits. But if it turns out that the problem that I'm having is my application is too frequently accessing the database, I get all of these alerts, but the root cause is completely different. Now I need to focus on the application and simply adding more resources to the cluster or adding more resources to the Postgres would not help to solve the problem. Or to take an even different approach, if my application has a different problem where it is doing bad data structures, it's looking some data, it's processing the data slowly, I will also end up with some of the same manifestations, but then again, I can fix it by simply adding more resources to the infrastructure. I want to actually create these scenarios and then show you how we identify the correct root cause so that the action that we take will actually restore the service and, of course, eliminate the alerts as well. So the point of this is to capture the knowledge rather than just collecting data and think about the previous set of potential root causes, focus on those root causes rather than just a set of alerts. Any thoughts or questions? Because I feel like I'm still going too quickly through this. Nope. Okay. All right. So for example, this is another illustration. Maybe I'm using too much PowerPoint. Eventually, I switched to a live demo as well. Like I'm showing how a particular set of alerts are observed, and then we basically can conclude that this application is badly written because it accesses the data too frequently, but all of these symptoms are caused by that root cause. Or I think I have another example where the root cause is basically bad mutex locking, and it causes all of these problems. So let me switch over a bit to this example because it might actually help you to illustrate what am I doing to create these problems, and then I'll switch over to show you what am I doing to solve these problems. So what we did with Chaos Mania is that we basically allowed people to use a simple YAML description of instantiating an application topology and instantiate the interaction or manage the interaction between those services. So after you deploy the Helm chart that I mentioned above, one of the commands is to basically kick off this boutique YAML plan. which basically is first going to make a call to the AD service and HTTP request, and then it's going to tell the AD service to allocate some memory. And then it's going to make a call to the cart service, and it's going to make a SQL query. Of course, you could make this a bit more sophisticated. And then it's going to push some data into a Redis queue uh, from that cart service. And then it's going to make a call to a current service, which is going to pop that from the queue, and it's going to allocate some more memory. And then it's going to make a call to a recommendation service that's going to, allocate some memory and burn some CPU. And then it's going to make a call to a shipping service, which is going to again make a call to a database. And in turn, it's going to call the product catalog. And this is where we are probably making the first things that people should not do is create a mutex lock, sleep for 3 seconds, and then unlock that mutex locks. Now, if you're doing this, you're probably freezing a bunch of other processing. I mean, this is a bit of a Mickey Mouse locking, but I think that unfortunately people do this in real life. And of course, they are slowing down all the rest of the processing while they are sleeping inside the lock, or maybe they are processing some data inside the lock. Really, what I'm trying to illustrate here is that without actually having to write any code, you can create interactions across different microservices, and both the services themselves as well as the infrastructure or middleware components. And if I create a heavier database query, if I push more data into Redis, or if I burn more CPU somewhere, I can create all kinds of interesting scenarios um, to observe, because one of the other things that we wanted to illustrate is that these chaos mania components are automatically out of the box instrumented for metrics, tracing, as well as logs. So all of these things are become observable. Maybe if I switch over so this is actually running in my environment. If I switch over to look at, for example, my tracing, uh, I can see that there is these HTTP calls being made. There is these Redis pushes that are being made and pops, and here we are sleeping in this thing for X number of seconds, in addition to doing other things. So you get basically all of the observability signals. You can collect all of these data using Tempo, but in any open telemetry tool. The problem is that now I still have to look at this and figure out what's actually going on. And of course, in different scenarios, this picture would look differently. And it's not obvious to me what is the actual root cause. So here comes Causely. If this environment and this application is also managed by Causely, Causely will not only take these symptoms, these manifestations, these alerts as an input for a number of applications, database servers, caches, nodes, Kubernetes services, but take these alerts as an input, and it identifies the actual root cause or root causes in the environment. One of these root causes that it automatically identified is bad data structure locking in this product catalog service. And it basically automatically created a causal structure based on the initial human knowledge that we captured, but instantiated without any learning, without any additional training, instantly in this application as soon as the application was discovered and the scenario was kicked off. And it's basically able to find a causal relationship between this root cause and all these yellow alerts that I'm getting, the various high transaction duration, high mutex wait time, high latency across multiple services, as the shipping service is calling the product catalog service, the front end is calling the shipping, and I think that we have even, of course, latency on the actual front end service as well. So really our goal here is to automate the process of, instead of looking at traces and trying to manually figure out what the root cause is. By the way, I didn't even switch to metrics because we're also collecting part of this information from metrics, being able to, in your head, put together the relationship between the various components, the metrics and the traces observed for those, is automatically identifying, where the problem is and what the problem is. Um, um, uh, and of course, in this case, if I want to change how I do mutex locking, I need to change the code, or I guess if I'm lucky, I can just sleep less here if I could. It would be that easy to fix an application problem, but effectively focus on the root cause instead of all the other alerts that I'm getting across the different services that end up being dependent on this service. Now, of course, we are doing this by in real time, instantly discovering the environment. We need to understand the dependencies between these services. So if I were to illustrate that, if I look at, for example, our front-end service, based on the combination of the OpenTelemetry instrumentation and other metrics that comes with our nice little Chaos Mania application. We know that we have a client that calls the front end that calls all of these services, that this currency service is consuming the key one topic from Redis, and this queue is actually produced by the card service, and of course, both of these services are accessing the actual Redis cluster to be able to do this. We also understand the layering relationships of how they depend on the underlying hosts, what containers are running in all of this. But and I think that any observability tool should give you, all of these nice service graphs and layering graphs, but that alone is not enough to actually figure out what the root cause is. So what we are able to do is actually sorry, applications. Sorry. We can actually reason about, what are all the potential problems that can happen for this application. This application can fail. If this application fail, it would cause errors across all of these dependent services. If this application was it's not a queue consumer, if it was a consumer, it would cause consumer lags on the topics. If it was, simply congested, it would cause, some latencies. But in the case of inefficient locking, it causes a set of different symptoms. And basically, by being able to see what are the symptoms that can be caused by different root causes, we can identify what is the current active root cause and to explain how this root cause is causing these different services. Now, if I were to change the scenario, obviously it would be a lot of fun to figure out other problems that I can reproduce and identify in the environment. Any thoughts so far, or am I still going too quickly?
No, I'm trying to understand a little bit like
Yeah.
so right now we're seeing the system. Is it like if I press on one of the issues that we see here, what would I see? Would it take me to the pod? Would it take me to the actual? Okay, would it
Yeah,
take
so we are actually trying to make this really easy to explain and to be able to get even more information. I think Shanto has even more suggestions on how we make this even more useful. But what you see, so let me explain a bit. So what you see here is a causal structure that shows the causality between a root cause and a set of alerts. These alerts can be from one or multiple different microservices, different components or databases. So I can have on the same product catalog microservice both a high transaction duration symptom and a high mutex wait time symptom, or I can have a different symptom on the communication between the shipping and the product catalog, or the front end and the shipping service. So these are different symptoms across different parts of the infrastructure, and we want to be able to show you more details of how did we, come to this symptom, but assuming that you think that, waiting, well, I made some really, long waits here. So we are, we don't want to wait on Mutex logs for say more than 20% of the time. Here I'm waiting for 3 seconds, which is significantly more than the amount of time I'm taking to actually process this data. Besides making these symptoms explainable, just as importantly, want to show how the combination of these symptoms are leading us to identify this root cause. In addition to being able to look at the symptoms, what I was doing earlier, I was able to also click on the actual individual microservices and then dig into both their dependencies in terms of how they communicate with other services, how they rely on the underlying infrastructure. And again, this is just to help people to trust our system, that our understanding of the topology is correct, the symptoms are correct, and based on that, the root cause that we identified is the thing that you need to resolve instead of chasing other signals or other alerts in the environment. So uh, I mean, I don't know what is more helpful, but what I usually like to spend time with is to look at a number of cases where we could say that, like, well, what happens if I don't have anything that's broken in the environment? Can I reason about what are the potential things that can fail, which you cannot do by correlating alerts? Because let's say nothing is wrong, there's nothing to correlate as an alert. Using causal AI, you could actually identify what if, for example, this Postgres database were to fail, what would be the symptoms, or if this Postgres database was congested, what would be the symptoms that I could observe, or if I ran out of connections, where would I observe problems, or if I look at this Redis, what type of problems I can have, what services would be impacted if this Redis cluster was slow, or what errors would I see if this Redis cluster failed, like, ran out of memory, filled up the disk space, what are the services that would die? So I could actually reason about all the potential problems even before they happen, which is an interesting thing, because if nothing is actually broken, you may want to think about, like, how do I understand the risk of a particular failure? How do I avoid single point of failures in the environment? And one of the benefits of causal AI, besides being able to explain an active root cause of a problem, is to be able to reason about potential problems before they occur, so that you might choose to change the architecture, take some different decisions, so that you basically avoid that failure, or you avoid the broad impact of that failure, even if one of these components were to happen. And I think without causal AI, it's really impossible to reason about the possible things that can happen, because everything is broken, but I can still understand what would happen if some of these things actually failed.
Does this work with some kind of alerting, or do I need to actively browse the system to do this? Can I set like a threshold for this?
So that is a good question. How do we operationalize this? And I'm actually kind of curious. Our goal is for the problems where we could ultimately remediate it by integrating into a GitOps workflow or automating some changes that can take to remediate or prevent an action. We basically have a remediate button. This is obviously can be clicked manually, but it can be automatically triggered as well. So the best case scenario is that you don't have to look at this because we are able to, having identified the correct root cause, automatically take action. Now, that is not the case when you need to make a code change. We are not currently changing the code, at which point you would want to get notified. And we haven't provided this yet out of the box, but the idea is that we want to notify you, for example, through a Slack message, or whatever means that you want to get notified. But the point is that instead of notifying you of these 9 different alerts, and maybe notifying different people responsible for these different microservices, we can only notify you about the actual root cause and possibly and preferably only notify the owner of that service who needs to take action. Or maybe we could say that these other services are also being impacted, so we could let them know that there is this thing going on, but they don't have to take an action because the root cause is in this service. So for the things that we don't automatically remediate, we want to reduce the noise, and also avoid the confusion between multiple teams that are responsible for different components, databases, Redis clusters, application services, so that they don't have to get alerted for every single threshold violation.
In your example, everything, all the application is located inside the Kubernetes. In the real world, applications are integrated and communicating with something outside. So in general, how you deal with the connections?
Thanks, Chantal. That is a very good point. We did not. We designed this platform to be agnostic to where the applications are running. We started to apply this to Kubernetes and cloud-native-based applications because the discoverability of those microservices is easier out of the box, and even the instrumentation of these services is easier out of the box. But we already have the ability with the same software to tap into a combination of data sources. For example, we tap into the cloud APIs like AWS's CloudWatch to discover an RDS database, or Confluent's API to discover the Confluent Kafka broker, Kafka clusters. And we are able to create these causal structures with the combination of services, maybe the business logic running in Kubernetes, and then some of the managed services, be that database or a broker running as a cloud managed service. And we're even looking at external SaaS endpoints. So, for example, if someone is communicating to, I don't know, Docker, or that's not a good example, GitHub, we are actually looking at what are the communications to an external SaaS endpoint. And if that external SaaS endpoint that we are not necessarily directly monitoring is slow or have errors, we are able to identify the malfunction, the congestion, based on the symptoms that we can observe from the things that are communicating with the external endpoint. So we definitely want to manage both your external managed services as well as the external SaaS dependencies as part of the root cause analysis and reasoning process. And we do this out of the box so that you don't have to, do anything special, install some special software, talk to GitHub, or talk to Grafana, for example. It's interesting what's going on here. Anyway, never mind. So, obviously sometimes these be slow, but anyway. So we designed this to be, managing hybrid applications, and we want to continue to add more support out of the box so that we can help you to run these hybrid applications in the combination of clouds and providers that we use. This is fun. You could look at, how, for example, traffic is flowing through a message queue, like who is the producer, who is the consumer of this. And in this case, this is still in cluster, but then I could look at, I'm basically consuming and producing to this queue, but then I'm consuming and I think producing to this other queue. And this actually, this is the producer, this is the consumer of these queues. So it's actually, I think, a lot of fun to look at these dependencies. Even more fun to actually use these dependencies to see that how various failures can propagate and what symptoms you may observe in different cases as you look at the combination of brokers, queues, topics, databases, microservices, external dependencies. I don't have anything running here. It's a simple thing that is part of the application that I showed earlier on how we are producing and consuming messaging in this queue. So I think that what would be great is to if anybody has any interest to dig further, you're of course welcome to try out these fun scenarios. There are a couple of other plans here that you could try. We've got a whole slew of sample applications that are pretending to be YouTube, where someone can upload a fake video, show a video, show recommendations on a video, and break a fake YouTube application, identify problems there. But probably even more interesting than the toy applications that we are providing as part of the sample open source project is to be able to see if our software can help you in your live environment identify real problems and help you to run applications better.
I want to know a little bit about the installation process, and
Yes.
Also like what kind of resources that it demands. I think.
Sure. So there's a couple of things. If you go to our website, we've got it's really simple. I'll expand on this, but basically, our, our software is provided as a SaaS service. The way to interact with your data sources is by installing basically an agent in your cluster. That agent is a relatively lightweight agent. It is a deployment that talks to Prometheus, receives OpenTelemetry, and a daemon set that also has the ability to parse out traffic from the individual nodes using an eBPF agent. We are not inventing our own eBPF code. We are using open source projects. But what gets deployed in your environment is the ability to integrate with your Prometheus, OpenTelemetry, Istio, other data sources. We actually have another public project that describes in a little bit more detail on how to install the agent, what are the optional values that you could provide as a Helm value file to point to your Prometheus endpoint, to be able to deploy an OpenTelemetry collector to send data, how to integrate with Istio. We basically support a number of providers out of the box. So if you're using a RabbitMQ, Redis, MySQL, MongoDB exporter, either for a self-hosted or a cloud-managed database service or message broker, will automatically discover them and make them part of our topology just by simply pointing to the Prometheus endpoints. I think I didn't write much about the AWS and GCP and Azure integration. I guess I should write something about that as well. They also support getting data from Datadog out of the box if someone prefers commercial instrumentation other than the open source instrumentation. I think I have some examples here on how to integrate with Datadog and how to integrate with custom metrics for observability. But anyway, so the point is that this is basically a piece of software that talks to your observability tools within your cluster. We are actually not sending this observability data back to our backend. The only thing that goes to our backend is a high-level representation of the service topology, the entities, the relationships, and the active symptoms, basically a Boolean indication of I have high latency here, I have a high CPU here. So all of the traces, all of the logs, all of the metrics remain in your premises. So it's a fairly small amount of data, really the minimum amount of data that's required for us to reason about the root cause. So both the agent is lightweight, easy to install. We provide as much as we can out of the box, and the actual data that we need to make this is minimal and not sent mostly out of your out of your premises. If that makes sense, Amir.
Yeah, thank you.
And I think I have some of these. I can share my PowerPoint. I'll send you a copy if that helps. But even better, if you guys have any questions, you want to try this, just let me know, and I'm happy to sign you up in RSS as another tenant. And you're welcome to try it anywhere, especially if it's a one of your clients that are struggling to troubleshoot complex problems. That's even more fun. But anywhere where you think that you could try out a couple of these scenarios, even any applications that you might have. I,
Any other questions, guys?
Great. Great. I hope this was helpful, and I'm really interested to hear anybody's feedback who wants to try Causely or wants to try it in your client's environment or want to try it in a test environment. And especially would like to learn more about challenging problems. Shemtov has been sharing quite a few that he is spending a lot of time troubleshooting, and that would be great to have conversations with others on the team as well.
So you'll send me the
Yes,
presentation, and
yes,
also I will add there your email address,
yes,
and
yes, yes.
I hope we will have some more. Uh, we don't have many Shemtovs, but we will have as good as I know from here. Yeah.
Happy to talk to anybody who is interested in learning more and trying it out. So thank you.
This was really interesting. Let me stop the recording.